Hi class, today we're going to start talking about section 3.6, and this is going to be a part 1 video because this section is a little long, and this section is on rational functions. Okay, so a rational function is a function of the form r of x equals p of x over q of x, where p and q are polynomials. All right, and we're going to assume p of x and q of x have no common factors. Okay, so first we're going to start with rational functions and asymptotes. So the domain of a rational function consists of all real numbers except where the denominator is 0. So for example, we're going to take the function 1 over x. So the graph of this function will look like this. 1, 1. So here at 0, there is a vertical asymptote. So what this means is as x approaches 0 from the negative side, the function f of x approaches negative infinity. And then on this side, as x approaches 0 from the positive side, the function f of x approaches positive infinity. And the domain of our function is negative infinity to 0 union 0 to positive infinity. And notice we have soft brackets. We don't have a hard bracket here because we do not include 0 in our domain. All right. So, and then when I was talking about from the negative side and the positive side, what we will actually write f of x approaches infinity as x approaches 0 from the positive side, and f of x approaches negative infinity as x approaches 0 from the negative side. And I think in past, when we talked about end behavior, we might have had like y equals positive or negative infinity depending on where x was approaching. You could also write y in your graphs and in your homework. That's fine. All right, and the line x equals 0 is called a vertical asymptote. And the line y equals 0, horizontal asymptote. Nope, I'm spelling this wrong. Again, why I was not an English major. Horizontal, there we go, asymptote. So you can notice up in our graph that the line also does not cross this area here. Okay, so moving forward, I'm going to draw some examples of some vertical asymptotes. So there are 4 ways we can have a vertical asymptote. So we can have I'm going to draw the line in blue. We can have y approaches infinity as x approaches a from the positive side. And then we can have this line is y approaches infinity as x approaches a from the negative side. And then we will have this graph is y approaches negative infinity as x approaches a from the positive side. And then our last possible vertical asymptote is, oh, all of these points have been a. Should have been writing that better. All right, and then here we have y approaches negative infinity as x approaches a from the negative side. And now there are 2 ways for us to have a horizontal asymptote. I'll call this point B. So the first way to have it is coming up this way. So this one is y approaches b as x approaches positive infinity. And then our other graph is y approaches b as x approaches negative infinity. And you see here, our graph can pass a horizontal asymptote. It's just the end behavior that gets closer and closer to it. Whereas with our vertical asymptotes, our graphs can never pass these lines. They're kind of like a bounding on our graph. So now we're going to work with transforming a new graph. Our new base function will be 1 over x. So we talked in previous lectures about transforming x to different powers, and now we're going to look at transforming a rational function. So So adding a number to the denominator shifts the graph left or right. So this also means that it will shift the asymptotes. So for example, if we have the function f of x equals 1 over x plus 3. So this will shift our 0 over from 0 to -3. We have our graph. We have our -3 here. We'll have our asymptote. And then we have our graph. Like this. So it shifted everything over. All right, so now let's look at another example. So now we're going to examine 3x plus 5 over x plus 2. So using long division, we can rewrite this as 3 plus -1 over x plus 2. So we've added 2 to the denominator, and we've scaled by -1. And then we added this 3 here. This is an external addition. Where this here, this x plus 2, this is an internal addition. And then our scaling is here. So that means if we start with our graph, or at least our axes, so 1, we shift by 2. So we need to shift to the left by 2 because we've added 2. So 1, 2, there's our -2. And then second, we're going to shift up by 3. There should have been a little shift over here. All right, so we have a 1, 2, 3. So by adding 3 externally, we have lifted where our horizontal asymptote should be. So I'm going to draw those asymptotes now. And then 3, we're going to scale by -1. And graph. So remember, our original graph was like this. So then we're flipping it. So by scaling it, it'll look like this. So then our graph will become something like this, where this is our new f of x. All right, so now I'm going to help y'all develop a procedure of how to graph like scary irrational polynomial functions. The main goal is to get a feel for how the work is, not knowing exactly what's going on at every single point. That's why we have an equation that will let us know what happens at any point we want. Graphing just lets us have an intuition of what's happening big picture. So to do this, to get this intuition, we're just going to work through a complicated example. So we're going to look at f of x equals 2x squared minus 4x plus 5 over x minus 1 squared. So 1, we're going to find a vertical asymptote, and I abbreviate vertical and horizontal asymptotes with just VA and HA because that'll help writing and making things quicker. You're more than welcome to do this on your homework. So this is where, this is where the denominator has its real zeros. So in our example, that is at x equals 1, because that's when the denominator will be 0. All right, and then our second step will be find horizontal asymptotes. And okay, so to do this, we're going to look at the leading terms. In both the numerator, oops, that's an M. Okay, in both the numerator and the denominator. So there's some different options here. So 1, if the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. Okay, so this happens if something like x to the m over x to the n, where m is strictly greater than n. Okay, so then second option, if the degree of the numerator and denominator are equal, the horizontal asymptote is a ratio of leading coefficients. So what that means is if you have ax to the n over bx to the n, that means that our horizontal asymptote is at a over b. Oh, whoops. Get rid of my pin function. There we go. All right. And then the third option is if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is at 0. So that's when we have x to the m over x to the n, where m is greater than n. Oh, did I switch that from the first example? I did. That's confusing. No, wait. Okay, that's in the correct direction. I just have the wrong less than or equal to sign. Sorry. Where n is greater than m. There we go. Okay, so in our example, the degrees are equal. So we have an asymptote 2/1, which is the ratio of our leading term, which just equals 2. And so going back to our original example at the top here, we had a 2x squared, and then when we were FOILing this out, we would have an x squared minus 2x plus 1. So it would be our leading coefficients would match. So you might need to FOIL out denominators or numerators to double check this leading term for our horizontal asymptotes. Okay. And moving on. Step 3. Find the zeros, if any, of our function. Oh, it should not just find the zeros. There's always a zero. Find the real zeros. Of our function. So we need to look for when the numerator has real zeros. Oops. Just a period there. All right, so in our example, (2x squared minus 4x minus 5). Wait, minus 5. Did I write the plus 5? Sorry. Plus 5 has no real zeros. Now I will show y'all with the quadratic formula why that's true. So if we look at 4 plus or minus the square root of 16 minus 4 times 2 times 5 all over 4. Well, this will lead us to a 4 plus or minus the square root of 16 minus 40 all over 4. Well, that means that this is negative. It's the square root of a negative number. Well, that means that it's complex. So for graphing, it doesn't matter. So for this example, we're going to stop since we know it's complex and it won't help us with graphing. But if I asked you to find the factored form, you'd keep going. All right, and then 4, we're going to find the sign of the zeros. Oh, sign of the values between 0, sorry. Find the sign of values and the vertical asymptotes. All right, so in our example, we just need to check either side of our asymptote. So since our asymptote is at, well, it's been a while since I saw the equation. So our asymptote is at +1, so I'm going to pick 2 and 0 to check both sides. So f of 0 equals, we'll get a 5 and a 1, which just equals 5. And then f of 2 equals, well, there we will get a 2 times 2 squared minus 4 times 2 plus 5 over a 2 minus 1 squared, and that'll give us a 2 times 4, which is 8. Oh, wait. And then that'll subtract us an 8, and then plus a 5 all over 1 squared is 1. So it'll give us 5, which is greater than or equal to 0. And I forgot, in the first example, it was important to find the sign of the values, not just the values. So we know that both of these are positive. So then we're going to determine our end behavior. Or I guess it's not end behavior, we're just examining the behavior near asymptotes. So this will tell us if the function is approaching positive or negative infinity and from which direction. So for our example, f of x approaches positive infinity as x approaches 1 from the positive side, because if we were to look at our problem, we would see that as you if you have a number bigger than 1, it's going to be a positive over a positive, so that'll give us a positive infinity. And same with if you do a negative 1, you'll get a 2 plus 4 plus 5 all over like the number 1. So that's a positive over a positive. So f of x approaches infinity as x approaches 1 from the negative side as well. So now we're going to graph. So our first step is, as always, to draw our axes. And we know our vertical asymptote is at 1, and our horizontal asymptote is at 2. And I like to draw these dotted lines as my asymptotes. It helps me know where like our graph can't go between. And we know that they are positive, and actually the value is 5 at 0 and 2. Plots his notes above our asymptotes here. So that means our graphs look like this. So there we go. That was the end of our example. All right, so now we're going to do another example, but we're going to go a lot faster this time. So we're going to look at x squared minus 2x plus 1 over 2x squared plus 3x minus 2. So first we're going to find our zeros. So the zeros of 2x squared plus 3x minus 2. Well, this will factor into 2x minus 1 and x plus 2. So our zeros are 1/2 and negative 2. So this means our vertical asymptotes are at 1/2 and negative 2. All right, so now we're going to find our horizontal asymptote, so that's next. So notice x squared over 2x squared. this becomes a 1/2 for our ratio. So our horizontal asymptote is at 1/2. Right, and now we're going to find the zeros of the numerator. So the zeros of x squared minus 2x plus 1, this factors into x minus 1 squared, so a 0 at 1. All right. So now when we check the values in between our vertical asymptotes and our zeros, I usually make a little chart like this, where I write them in order on a number line. And I will check the values in between. So I will probably pick a -3, a 0, a 3/2, and a 2 to check my values at. So just looking at our above problem, let's look at it again. So if we were to use -3, we would get a 9 plus 6 plus 1, so that's a positive, over, and then we get a 18 minus 9 minus 2. Well, that's still positive. So that means the whole thing is positive on this side. And then if we were to do 0, we'd get a 1 over -2. So that's a positive over a negative. So that implies that the whole thing is negative. And then if we were to do 3/2, we would get, if you just quickly run through, we will get a positive over a positive. And then same with 2. If we were to plug that in, we would get a positive over a positive. Yes, perfect. So then going forward, we will, now we are going to graph our function. Now we know what the values are in between our, we often call these cut points, our zeros and our asymptotes. So if we start with our axis, so we have a point at -2 and another one at 1/2. These are our asymptotes. And then a point 1/2 here. That's our horizontal asymptote. And then if we plot our zeros first, we know there's a 0 at 1. And that's our only 0. So then we also can plug in our y-intercept pretty quickly by just plugging in 0. And we see that it is a -1/2. And then we need to check our end behaviors real quickly. But since we know that there's a horizontal asymptote, that means that it will approach these different areas. It'll approach the asymptote. So we'll graph, touch, and come to the asymptote. And this one will come up, touch, and just kind of come down to this other asymptote. And then here we'll have kind of blocked in. So the asymptotes generally kind of will divide our graphs up into quadrants like this, where we know where they all end up. So that's the end of our graph and the end of this lecture. I will continue with this section in our next lecture. It was just kind of long, so I didn't want to have like an hour-long video for y'all to watch. All right, thanks so much. Talk to you later.